Hey, honors physics students, this is Mr. Everly talking to you. Um, Not quite in Canada yet, but a few days before, making a couple videos for you. Our next unit is on electrostatics and electric field. Unfortunately, I'm not there, so I won't be able to get into some of the discussions with you and some of the experiments and demonstrations, which we'll have to handle when I get back. So I've made a series of videos for you to handle a little bit of the concepts and a little bit of the math while I'm gone. So you can kind of work on that. And when I return on Wednesday, we'll do some demos and hopefully make this stuff a little bit more realistic for you. This unit is all about forces between charged objects. You already know about gravity and how it works. When you have two objects with mass, they attract each other due to an unseen gravitational force between them. This is also true for two objects with electrical charge. Electrical forces between objects, like the forces between electrons or the forces between protons, basically rule our daily lives. The reason that you can sit in your chair or set your hand on your desk without passing through is due to the electron to electron repulsion of the atoms in your body and the atoms in the chair or desk. Everywhere you go, the electrical force is actually more important to you than the force of gravity. So a couple of concepts have to be brought out that you already know. For example, the concept of charge. If an object is positively charged, um, another object is negatively charged, we know those two objects attract because unlike charges cause an electrical attraction between the two. If an object is positively charged, usually what that means is it has fewer electrons than normal. Most objects in the room are neutral. They have just as many electrons as they do protons. But if you take a few electrons away, that object becomes positively charged. If you add a few extra electrons to something, it becomes negatively charged. So it's usually the electron, which is the charge carrier. Excess electrons means negative charge on the object. An absence or deficiency of electrons means the object has a positive charge because it has now more protons than electrons. The person who came up with the idea of positive and negative was actually Benjamin Franklin. Not only was he um, one of our founding fathers, he was a world-class physicist and did a lot of experiments on electricity and separating charges, and came to realize that there are two kinds, positive and negative, and gave them those names. The symbol for charge, mathematically, is Q. So it can be a lowercase q like mine here, or an uppercase Q. It really doesn't matter. The units of charge are the Coulomb, named after Augustin Coulomb. Okay, abbreviated with a capital C. The smallest charge you can get is the charge on one electron, or the charge on a proton. It's actually the same. Electron obviously negative, proton positive. So we call it the elementary charge. The elementary charge is 1.602 times 10 to the negative 19 coulombs. So the charge on one electron is negative 1.602 times 10 to the minus 19. The charge on a proton is positive 1.602 times 10 to the minus 19 coulomb. The charge on a proton and the charge on an electron are exactly the same, but obviously opposite. It takes as much, if you take a beach sand in your two hands and lift it up, you hold about 500,000 grains of sand. But one coulomb is 6.25 million electrons. For example, there's 8,000 coulombs of charge in your car battery. you had 1 grain of sand for every electron in your car battery, it would cover the entire Earth with sand. Now, when you have charged objects, they exert forces on each other. So let's go back a minute to gravity. You have an object with a mass, another object has mass m2. The distance between them we call r. They pull on each other. They tug on each other with a gravitational force equal to F, which is equal to G m1 m2 all over r squared. And we learned that G is the universal gravitational fudge factor, which has a value of 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. Okay, the units are just to make the final units be newtons when you use the equations. Don't get all excited about the units. Just note that that is a very, very small number. If you've got two objects with electrical charge, so let's say you've got a positively charged object, call it Q1, you have a negatively charged object, call it Q2. The distance between them is R. The force on which they tug each other is equal to K Q1 Q2 over R squared. So you look at those two equations and you say, oh my gosh, it's basically the same thing. The difference is, instead of talking about masses, we're talking about the amount of charge on these objects. Another huge difference is that this constant here for gravity is tiny. It's really small. 10 to the negative 11 is like 0.0000000000667 Newton meter squared per kilogram squared. This guy here is actually 9.00 times 10 to the 9 Newton meter squared per Coulomb squared. So that is like a 9 with 9 zeros. 9,000,000,000,000. So this is 9 billion, and this is a 667 with 10 zeros in front of it in a decimal place. So the difference between these two numbers is 10 to the 20th power. So looking at these two numbers alone, the electrical force is so much stronger than the gravitational force. It's like 10 billion times stronger than the gravitational force. Okay? Next, we have to be able to use this equation to solve some problems. Okay, so find the force between two charged objects that are 0.2 meters apart. The objects have charges of +5 microcoulombs and -4 microcoulombs. So here's the situation. Got a positive charge, Q1, 5 microcoulombs. You've got another negative charge, call him Q2, -4 microcoulombs. Okay. Our equation is F equals K Q1 Q2 over R squared. Distance between these two guys is R. So R is 0.2 meters from center to center. Don't include the negative sign in the equation, because what we have to do is look at the situation and determine ourselves what the direction of the force would be. So for example, because these two guys have opposite signs, the positive guy is going to feel a force this way, and the negative guy is going to feel a force this way. Now, the magnitude of those two forces are exactly the same. We only have one equation to find those two forces. If the question is, what's the force on this guy, it's going to be negative, pointing to the left. If the question is, what's the force on this guy, it'll be positive, it's pointing to the right. So use the diagram to determine whether the force is positive or negative, not the numbers in the equation. So So when I punch the numbers in, I'm going to say, okay, K is 9 times 10 to the 9 meters squared per coulomb. Q1, micro means 10 to the minus 6. So when I write it in, I'm going to have to write 5 times 10 to the minus 6 coulombs, because we need this guy to be in coulombs, not microcoulombs. Likewise, 4.00 times 10 to the minus 6 coulombs. Again, change it over from microcoulombs to coulombs. Divide the whole thing by the distance between them, squared, and that's all there is to it. Punch this through your calculator, you get 4.50 newtons as the force. Okay? 4.50 newtons acting on this guy to the right, 4.50 newtons acting on this guy to the left. That entire example. Another example. A force of 8.70 times 10 to the third newtons exists between a charge of 305 microcoulombs and 775 microcoulombs. What's the distance between the charges? Alrighty, so we've got a pair of positive charges. Okay, Q1, 305, Q2, 775, both in microcoulombs. The distance between them is unknown. The force on them is repulsive. They push each other away. Okay, the force equation is K1 Q2 over R squared. So if I multiply both sides by R squared and divide both sides by F, get this look at. Since I'm after R, not R squared, let's square root both sides. So R is equal to square root of K times Q1 times Q2 all over F, which we know is 8.70 times 10. Okay, punch it out. I am getting 0.494 meters as the distance between two charged objects. Okay, example 3. 3 charged particles are arranged in a line as shown. Calculate the net electrical force on particle 3 due to the other 2 charges. This first guy has a negative charge of 3 microcoulombs. This guy a positive charge of 5 microcoulombs. This guy a negative charge of 4 microcoulombs. Now notice we don't have to calculate all the forces involved. All we care about is the net electrical force on particle 3 due to the presence of the other 2 guys. So we're only concerned with the forces on this guy. So Q3 is experiencing a force because of the presence of Q1. They're both negative. So that means Q1 is going to repel Q3. So we'll call that force 1 due to the presence of Q1. Does Q1 feel a force due to the presence of Q3? Absolutely, but we don't care. It says calculate the net electrical force on particle 3. So Q2, what does he do? Well, he's positive, Q3 is negative, so we know that he's getting attracted by Q2. So I'm going to call that force 2. Okay, we're going to use the equation twice. F1, 9 times 10 to the 9 Newton meter squared per Coulomb squared. Again, I'm using the equation. Okay, 2 charges. In this case, it's charge 3 and charge 1. Okay, over R squared. So I've got my K, I've got charge 1, which is 3 times 10 to the minus 6 coulombs. Notice I don't even bother putting the sign there. Q3 is 4 times 10 to the minus 6 coulombs. Distance, half a meter squared. Result, punch it through, 0.432 newtons. Okay, notice it's in the positive direction. The answer is positive 0.432. 2. Okay, using the same equation, except I'm going to do Q2 and Q3. 9 times 10 to the 9, 5 times 10 to the minus 6, that's Q2. Q3, once again, 4 times 10 to the minus 6. Divide the whole thing by 0.2 distance between them, and don't square it. Punch it out, and you get 4.50 newtons. Notice this is in the negative direction, not because of the signs on the charges, but because of the direction of the force, which we've already determined. Okay? Then you add the two up. Say, okay, he's in the positive direction, he's in the negative direction. We sum them up. We get a negative 4.07 of force. Okay? Net force on this guy, negative direction. Q2 is big, and it's also really close. So it kind of overpowers F2, overpowers F1. Okay, what if you come up against one of these? Now, I'm not going to do all the calculations for you, but here it says calculate the force on Q2 due to charges Q1 and Q3. So if I've got Q2 here, and I'd like to know what the net force is on him, I'm going to say, okay, Q1, Q2 are both positive. Force 1 is this way. Q2 and Q3, he's positive, he's negative, so it's going to attract him. There's force 3. So can we calculate those two forces? You bet. When we calculate the two forces, we end up with a force in this direction. Okay, so let's say I do my force 1, K, Q1, Q2 over R squared. Okay, distance between them is 0.3 meters. Q1, Q2 we know. We punch it out, we get 325 newtons. Force 3. Okay, find the force between these two guys. We know the charge, we know the distance, it's 0.52 centimeters. Punch it out, we get K Q3 Q2 over R squared. R is now 0.52. Get 143. Okay, so one way to state the answer would be the force on these guys would be 143 I hat minus 325 J hat. That's it. There's our answer. Okay, so calculate the forces on these guys in 2 dimensions. You can do an I hat, J hat if you wish. If you want to know the magnitude and direction of the net force, you can do a Pythagorean theorem, inverse tangent. Not going to cover that right now. All right, so these are the examples that will hopefully allow you to do some Coulombs law calculations.